We're looking at Chapter 7, Logarithmic Functions, specifically Section 7.2. We are going to evaluate logarithmic expressions by writing them in equivalent exponential form. So if you recall, we're just going to look back at the functions we've been looking at. In Chapter 5, we looked at linear, quadratic, and cubic functions, and we analyzed and investigated specific characteristics of the graphs and of the equations. In Chapter 6, we looked at an exponential function, and in Section 7.1, we looked at the logarithmic function and the natural log function. If we're looking at a logarithmic function versus an exponential function, you can see that the logarithmic function, right here, is a reflection of the exponential function. And we can see that the x-coordinate of an exponential function is the y-coordinate of its logarithmic function. So recall, a logarithmic function is a function of the form f of x equals a times log x base b, where a cannot equal 0, b is greater than 0, b cannot equal 1, and also x is greater than 0. The natural logarithmic function is f of x equals a times ln x, where in this case the base is the irrational number e. The logarithmic function versus an exponential function. So you can use your calculator and evaluate y equals log x to complete the table of values below. Then we're going to express the function in exponential form. So if we put in our calculator log of 1, we will get 0. Log of 10 will be 1. Log of 100 would be 2. 1,000 would be 3, 4, 5, 6. Now we're going to express this in exponential form. Since this log is base 10, this will be base 10. If there's no base indicated, it is base 10, and that's the base of a logarithmic function that we can calculate using our calculator. That and of course the natural log base e. And writing this in exponential form, we have that 10 to the power of 0 is equal to 1. We have 10 to the power of 1 is equal to 10. We have 10 to the power of 2 is equal to 100. It's 10 to the power of 3, and so on. So we can write these numbers in exponential form. To go from logarithmic form to exponential form, we have specific things, or specific parts of the log equation. We have the base. We have a number here called the argument. And this will be the exponent when we change it into exponential form. So if we take something of this form and change it to exponential form, the base is here. What it equals, the e, is in the exponent, and the argument is what it's equal to. So for example, log 27 base 3, we cannot calculate this with the calculator since it's not base 10 or base e. If we're trying to evaluate this expression, we'll set it equal to x, and then we'll write it in exponential form. So our base is 3, our exponent is x, and that equals 27. For a logarithmic function of y equals ln x, in this case, our base is e, our exponent is y, and our number that it's set equal to is x. So let's have a look at an example. We have, in this case, this is in logarithmic form. The base is equal to 2. The exponent would be equal to x, since this is b, n, and e, and the n, which would be 4. Now we're going to put this in exponential form. In exponential form is represented, the base to the power of the exponent is equal to a number. So we have 2 to the power of x is equal to 4. Many times we could use this base to the power of what it's equal to is equal to the argument. And so we would continue as from what we did in chapter 6. We'd have 2 to the power of x is equal to 2 to the power of 2. So x would equal 2. In the next case, we have log of 1,000 is equal to x. Now we can compute this on the calculator since it is base 10. Recall that if the base is not there or indicated, it is base 10. And we can calculate any log with base 10 or e on the calculator. And so in this case, we'd have the base is 10. So we'd have the base is equal to 10. The exponent is equal to x. And the number is the argument, which is 1,000. So we have log of the argument, and I'm going to call it n, base b, is equal to the exponent for logs. That's the logarithmic form. So we're going to take the logarithmic form and write it in an exponential. That'll be 10 as the base, the exponent would be x, and that would equal 1,000. And so 10x equals 10 to the power of 3, so x equals 3. If we look at the next question, we have a natural log. And of course we know here the base is going to be equal to the irrational number e. The exponent will be the y, and the argument is the number. So we have e to the power of y would equal x. Here we'll do the reverse. We'll write an exponential form into logarithmic. So we have the base, the exponent, equals the number, and we're writing it in log form. So we have log of a number, or the argument, base is equal to the exponent. And so here, the base equals 5, the exponent is equal to x, and the number equals 1 over 125. And so we're writing it in logarithmic form. We'd have log of 1 over 125, base 5 equals x. In the next example, we're writing it in logarithmic form again. This is given to us in exponential. So the base is equal to 9. The exponent is equal to x. And the number, 729. And so we write it in logarithmic form. Log 729 base 9 is equal to x. Here we have the natural log. Base is e. And so we can write this one. If the b is e, we can write this one as y is e. So we have ln 9 equals y. So in order to evaluate a logarithmic expression, we're going to convert the logarithmic expression to its exponential form. We'll set it equal to x and solve. So we cannot evaluate log of 1 over 27 base 3, since it's not base 10 or base e. So since we do not know what it is, we'll set it equal to x, and we'll change to our exponential form. We have the base and the exponent will equal the number. So we have 3 to the power of x equals 1 over 27. 3 to the power of x equals 3 to the negative 3. X will equal negative 3. So here we have a log logarithmic form again. We cannot evaluate this since it's not base 10 or base e, so we must convert it to its exponential form. We can set it equal to x first to help us. So if we set it equal to x, that will give us 1/4 x would equal 64. And so now we would solve this exponential equation by setting both sides equal to the same, have the same base. This would be 4 to the negative 1 all to the x will equal 4 to the 3. And so negative x would equal 3. X equals negative 3. In our last example, we have the log of negative 4 base 2. This is undefined. It's undefined since the argument is less than 0. But let's attempt it anyway. If you look here, we will set it equal to x, as with the others. And so we'd have 2 to the power of x would equal negative 4, in which we cannot find an exponent that will equal negative 4. Let's have a look at another example. Here is the pH scale in chemistry used to measure acidity of a solution. The pH scale is a logarithmic function of base 10. The logarithmic scale is useful for comparing numbers that vary greatly in size. The pH is defined by negative log x, where the concentration of ions is x. The solution is measured in moles per liter. And so, the first, it asks us if, it says the hydrogen concentration of a solution, so it's given us what x is, and we have to calculate the pH. So in this case, pH would be equal to negative log of 0.0001. Since this is base 10, we can calculate this on the calculator, and you'll get the pH to be equal to 4 when we put it on the calculator. It says in question B to use the pH scale shown, and there is no pH scale shown. It is on, the pH scale is on page 433 of your text. Page 433 of your text. To calculate the hydrogen ion concentration of lemon juice. So lemon juice will have a pH of 2. So we're going to say now 2 is equal to negative log x. So we're trying to find the hydrogen ion concentration. Now, first we're going to move the negative on the other side. So negative 2 is equal to log x. We're solving for x, and in this case, we're going to write it in exponential form. We have base 10 here. So 10 to the power of negative 2 is equal to x. This will give us 0.01 is equal to x, is a hydrogen ion concentration. Let's continue with the example and look at C. In C it says, in terms of hydrogen ion concentration, how much more acidic is a solution with a pH of 1.6 than a solution with a pH of 2.5? So let's look at solution A. And we have a pH of 1.6 will equal negative log x. That will be negative 1.6 would equal log x. We're going to solve by x first by changing it to exponential form. That'll give 10 to the negative 1.6 will equal x. For solution B, we have the same procedure. The pH is 2.5, and that will equal negative log of x. So negative 2.5 would equal log x. let's change it to exponential form. Remember, it's base 10, so it'll be 10 to the power of negative 2.5 will give us x. Now we have to figure out how much more times, how much more acidic is solution A than solution B. So to do that, that would give us 10 to the power of 1.6 over 10 to the negative 2.5, and this will give us 7.9. Here we can evaluate some logarithmic expressions, and to do this, once again, we're going to set each expression to x equal x. So this would be 3 to the x would equal 1/9. Of course, that would be 3 to the x would equal 3 to the negative 2. So x equals negative 2. We can see now that if you look at the base and look at the argument, then we may be able to predetermine without going through this procedure right now. So I know that 2 to the power of negative 3 will give me 1/8. So therefore, this expression would be negative 3. Let's just test it. We have that set to equal x. So it'll be 2 to the x would equal 1/8. 2 to the x would equal 2 to the negative 3. And of course, x would equal negative 3. So in our next one, we have, this would be, to be evaluated would be negative 3 as well. And this one would also be negative 3. So it says determine the concentration of hydrogen ions in each solution. Apple juice with a pH of 3.1, tomato juice with a pH of 4.2, and milk with a pH of 6.5. Once again, for each, we will have to, 3.1 will equal negative log x, and we'll put the negative on the other side, and then we'll change to an exponential function. So 10 to the negative 3.1 would equal x. We have for B, change color here. For B, we would have 4.2 would equal negative log x. So that would be negative 4.2 would equal log x. 10 to the negative 4.2 would equal x. And that would be the hydrogen ion concentration for tomato juice. And last, for milk, we would have C would equal 6.5 would equal negative log of x. So negative 6.5 would equal log x. And, of course, we cannot determine that. We have to change it to exponential form. Here, the same type of question. We have a car battery would have pH of 0, and distilled water would have a pH of 7. Distilled water is pH of 7, ammonia a pH of 11. And so if you look at, if we first find the ion concentration for car battery, we would have 0 would equal negative log x. So 10 to the power of 0 would equal x. So that would be 1. For distilled water, we'd have, it has a pH of 7 would equal negative log x. Negative 7 would equal log x. So 10 to the power of negative 7 would equal log x, or would equal x rather. So to determine how much more acidic car battery is in distilled water, then we would have 1 over 10 to the negative 7. This would give us 10 to the 7 times more acidic. If we look at how many times more acidic distilled water is than ammonia, we have, once again, distilled water. We know distilled water would be, X is going to equal 10 to the negative 7 from right here. Ammonia, we have 11 will equal negative log X, and so negative 11 would equal log X, and so 10 to the negative 11 would be X. So how much more acidic is distilled water than ammonia? We have 10 to the 7 over 10 to the negative 7 over 10 to the negative 11. This will give us 10 to the power of 4 more times acidic. Let's look at another example. If we're looking at a expression that involves 2 logarithms, and we're trying to determine or trying to evaluate such, we can take each expression and set it equal to X. So we have log 32 base 2 would equal X. This would give us 2 to the power of X would equal 32. 2 to the power of X would equal 2 to the 5, so X would equal 5. That is, this part of the expression is equal to 5. And as you can see, that we know this since 2 to the power of 5 is 32. That would give this to be 3. So 5 subtract 3, this expression would be equal to 2. Here we have, since 5 to the power of 2 is 25, this would give us 2. And subtract 5 to the negative 3 would give us 1 over 125. That would be negative 3. This would give us 5. In summary, the value of a logarithm can be determined in one of the following ways. First of all, by setting the logarithmic expression equal to y or x or to another variable and write the equivalent exponential form. Then to determine the exponent to which the base must be raised to get the required number. Yet if the base, another method is if the base of the logarithm is 10 or e, you can use a scientific calculator. Remember, when you are changing from logarithmic form to exponential, that the base would be the base of the exponent, of the power rather. What it's equal to would be the exponent of the power, and the argument is what it's equal to.